Yesterday, we talked about, conduction current as a type of current that goes into conductors, basically, okay? And we said it's the conduction current, you can consider it as being sigma multiplied by E. So here, after all of these calculations, what we got was that you can say J is equal to sigma E. And sigma is the conductivity of a material, okay? We said there are different ways to express the conductivity of a material. You can say what is the volumetric charge density of the electrons, and then how mobile they are. Mu E here is the mobility of the electrons. So conceptually, that makes sense, right? Depending on how much free electrons you have, how mobile they are, how fast they can move, that would tell you how conductive that material is. Now, let's do a little practice and see, here it says the unit of sigma is Siemens per meter, or 1/ohm per meter. Now, let's see if we can derive that. So here I'm going to do some unit calculations. The first thing we said is that, let's say sigma for a perfect conductor is minus rho VE, right? Mu E. Correct? Minus rho VE mu E. We said that because for a perfect conductor, we have more electrons, considerably more electrons, so we can just assume that this is our case. And then this is equal to NE NE mu E. Or in another way, we could have said this is, not this, but we can say, there's another way to say this, and that is that J is sigma sorry, my brain is short-circuiting. What I wanted to say was this one. Mu E, UE, the velocity of the electron, okay? So here we have UE being UE E. This is the formula I want to use. So I'm going to use this one first, actually, to derive the unit of mu E. Okay? And then I'll plug it in here to find sigma, the unit of sigma. Okay. UE is the drift velocity, right? We call it drift velocity. What is the unit of a velocity? Go ahead. Yes, thank you. So this is meter per second is equal to, mu E is the one that we want to find. And then what is the unit of E? What's that? Volt per meter. Volt per meter. So the unit of mu E is going to be meter squared volt dot second. Now we are going to plug this in here. So sigma is minus rho V E mu E. And the unit of sigma is going to be coulomb per meter to the power of 3 multiplied by meter over 2 meter squared volt dot second. That is going to be coulomb over meter voltage second. What is coulomb per second? dq over dt. What is that? You want to say? Yes, exactly. This comes from I being dq over dt. This is amps. So this is equal to amp volt meter. What is amp over volt? It's the reverse of volt over amp. What's that? Voltage over current. What is that? Yes.
Resistance.
What is the unit of resistance?
Ohm.
Thank you. So this is 1 over ohm. So this is going to be 1 over ohm multiplied by meter. Or in another way, Siemens per meter. So that's how we get the unit of sigma. Any questions? Now let's solve an example here. Okay, it says we have a 1 millimeter radius copper wire, copper being a perfect conductor, with conductivity of 5.8 multiplied 10 to the power 7 Siemens per meter, electron mobility. So let's break this down. This is sigma. Electron mobility is mu e. Subjected to an electric field of 20 millivolt per meter, that's amplitude of E. Electron charge 1.6 this coulomb. It's asking us, what is the volume charge density of the free electrons? Rho V E. Rho VE was, if you remember from here, we can use this formula, that sigma is minus rho VE. So we can say this is minus sigma over mu E. So this is going to be, or plus, no, actually minus. So minus 5.8 to the power of 10, 7 over 0.0032. And this is going to be coulomb per meter cubed. You can later simplify this number. And it should be negative because our charge density is charge density of electrons. Next one, it's asking about the current density, J, which is equal to sigma E. So amplitude of J is going to be sigma 5.8, 10 to the power of plus 7, multiplied by 20 millivolt. And then that is going to be 5.8 multiplied by 20, which is going to be 1.16. 10 to the power of 6, if I'm not wrong. And that's ampere meter squared. Or 5, yes, I think so. Now the current flowing in the wire, I, is J dot ds, or if it's uniform, J multiplied by area. 1.16, 10 to the power of 6. This is 1 millimeter, with the area being pi r squared, pi multiplied by 10 to the power of minus 6. Pi multiplied 10 to the power of minus 6. And that's going to be 1.16 pi ampere. The electron drift velocity, UE, is going to be what? We just reminded ourselves of this one. Minus mu E, E. Right? Minus mu E, E. So if you're looking for the amplitude of it, it's going to be amplitude of this. So 0.0032 multiplied by 20, 10 to the power of minus 3. That's 3.2 or 6.4 multiplied by, oh, who knows how many? zeros. So this is 3.2 multiplied 10. And this is 10, so 64. And that is meter per second. Is the mathing? Is it correct? 6.4, 3.2 minus 3, and then minus 3's cancel each other. Right? Good? I think so. Now, the volume density of the free electrons. Volume density is Ne. It's the number of electrons per volume, per unit volume, let's say. Okay? And that's going to be rho VE over E. So we found rho VE to be minus 5.8 10 to the power of plus 7 over 0.0032 over 1.6 10 to the power of minus 19. And this is number, or not number because number is unitless, 1 over meter cubed. I brought this because I haven't simplified it to here. So it's simple, it's just a lot of equations. So it's just better like to remember the physics behind them, you know, that what depended on what, and you know, the drift velocity definitely depends on the mobility and the amount of electric field that you're applying. That's the only suggestion I have. Any questions? So in fact, you can see that like if you calculate this number, this is a huge number actually. Let me just calculate it. So we have 5.8. Let me just go scientific. So we have 5.8 over 1.6 over 3.2. So that's 1.13, 10, 7, 3, 19. So copper in every meter cube. What's happening to this guy? Okay, in every unit volume of copper, we have 1.13 multiplied by 10 to the power of 29 electrons. That's what it means. So it's just better to, you know, change the unit volume to perhaps like micrometer per square, micrometer to the power of 3. So that like it would make sense that every micrometer by micrometer by micrometer of that copper, how many electrons we have. Any questions? So now that we know perfect conductors with infinite conductivity have that many, you know, electrons, what would happen if we apply some external electric field to them? So we have lots of electrons here. One here, lots of them, like just go as big as you can imagine. Okay? Now, as soon as you apply that external electric field, what happens to these electrons? No suggestion? How do they feel? Let's say that. What do they feel? Do you want to try it? Yes, go ahead.
Like a force in the opposite direction of the ocean field.
Thank you, yes. They would, all of them would experience an Fe on them that is opposing the electric field outside. Because Fe is QE. And since our Q is electron with a negative charge, it's going to be on the other way. So since the electrons are super mobile, you know, and they have no bound in a conductor, that's hence the infinite conductivity, that's what it means, that they can move freely, basically, and there's lots of them. What would happen is that all of these electrons, because of this force, they will all accumulate on this side of the conductor. So we would have E, lots of E's, like a lot of negative fields, negative charges. And on the other side, every time the electron left, they would leave a positive charge behind. And this is our external E. So now that we have negative charges here and positive charges here, in between them, an electric field, E internal, gets created. And since we have many electrons like this, what would happen is that E internal becomes exactly equal but opposite direction of E external. Just because if it doesn't, electrons would still keep moving, you know? So the system never stabilizes. The only way for this system to stabilize is if the internal field cancels out the external field completely, so that inside this conductor, E total inside would be 0. So that tells us, reconfirms with physics, why we said even though sigma is infinite for perfect conductors, the electric field must be 0 inside them. Remember yesterday? The only way that current would be limited in the perfect conductor was if E was 0 inside the conductor. But now, beside math, we have a better reason, we have physics behind it, that the only way that the electrons would be stable on the edges, on the surfaces of the conductor is when the electric field inside is completely 0. This tells us, beside this point, this is very important, because E total inside is 0, Gauss's law would tell us that the Q inside is 0. So E inside the conductor is 0. So Q inside must be 0. That means that Q always goes to the surface of conductor. Every time you try to inject some current to charges to a conductor, it would immediately go to the surface. It distributes itself on the surface. It never goes inside the conductor. Let's, for example, talk about this case. let's say I have a sphere, and I try to bring some charges with, let's say, something like a plastic pod or something on it. Now, knowing that inside this conductor electric field is 0, how does this Q distribute itself on this sphere? Where do the charges go? Do they go inside or on the surface? Please, somebody.
Surface.
Surface. Now, do they distribute uniformly or non-uniformly? It should be uniformly, because that's the only way that the electric field inside is going to be 0. They would cancel each other's electric field. So this is a uniform distribution. And then now, if I consider a Gauss's law that, okay, I have uniform charges around here. Let me just bring all of this up. I hate this. Why does it? I just wrote uniform distribution, okay? Now, if I want to draw the electric fields, every time we have positive charges, they act like a source for the electric field, right? So the electric field is going to look like this at every point. And it must be perpendicular to the surface of this sphere. That's the second thing we know, that conductors are equipotential and the electric field is perpendicular to their surface. Let's just say that I drew this uniformly. Maybe not. The last one is too much. Okay. So the electric field is going out uniformly. The charges are distributed uniformly. Now, what if the shape wasn't symmetric like this sphere, and it was something like this? Thank you, but not thank you. Okay. So let's say it was something like this. This was a conductor that looked like that. Again, the charges would go on the surface, nothing inside. So Q inside for both of these is 0, E inside is 0. The same thing for this one. Q inside must be 0, E inside must be 0. Now, tell me, does it distribute uniformly or non-uniformly? Till I figure this out, you have time to think. What do you think? Uniformly or non-uniformly? Okay, so it's going to be non-uniformly, but can somebody say, where would I have more charges and where would I have less? Any guesses? Any guesses welcome. Where would I have more charges? Go ahead.
The sides, longer sides.
The longer sides, I would have more charges. Here.
Yeah, like away from the quarters.
It's reversed. Okay? but thank you for speaking out. Okay, so we have more charges on the corners. And then less charges where we don't have edges or corners. And the reason is that, think of it that, you know, every corner we have, the electric field must be perpendicular to it. In order for this field to be perpendicular, you would have much more charges to go. Or another student in the other class gave a very good reason, that in order for these ones to cancel each other out, cancel each other's fields out inside, you would have a more accumulation of charges there. The distance is closer. So you would have much more here. And the same thing. And less density of the electric fields on that side. Okay. Now let's move on to, that was the case of perfect conductor. For perfect conductor, because we had infinite number of electrons, and they were infinitely, you know, they were unbounded, we have the internal electric field would be quite as strong as the external one, and they would cancel each other. But in the case that sigma or conductivity is limited, then the story is different. For example, when we are applying outside voltage, like a voltage source here, it's as if we are applying an external electric field. So this is positive, this is negative. Which direction is the electric field here? This is the positive voltage, this is the negative. If I wanted to say that this is the electric field, the electric field goes from in the direction of reducing the voltage. So it's as if we have an E external in this direction. Now, again, because it's a conductor, we still have electrons moving. You would still have some charges here and the positive ones on this side. But what happens is that the electric field inside that is being induced or created is not going to be as strong as the external ones. So it doesn't completely cancel the external one. In fact, it is going to be less. And that's why E inside, E total inside, would not be 0. When this happens, when the E inside is not completely 0, it's as if we have a resistance by that conductor. Because if it was infinite, right, no resistance, every current was just going through. But the finite conductivity would introduce some resistance. So we can say this is as if we had a resistance value here. And this resistance value can be derived by saying, okay, R is equal to V over I. V being, let's say this is point positive, this is point negative. I'm going to bring this here. The V that we have here is the positive voltage difference, okay? And it is going to be minus P negative to P positive. Or let me write it in another way. It is VP positive minus VP negative over I. And that's equal to minus E dot dl from P negative to P positive. And I can be written as J dot ds, where J can be replaced by sigma E. And if I call this cross-section A, and the length would be L, this would depend on L, and this one would depend on the cross-section area, the denominator. So that's how we can define the resistance of a finite sigma of a conductor, basically. Equivalently, we have R prime, which is resistance per unit length, and that's R over L. It's ohm per meter. That's resistance per unit length. And then sometimes you can even define G as, opposite of R, which is conductance. Instead of resistance, we say conductance, and that's I over V. And this is 1 over O or Siemens. And then equivalently, you can say conductance per meter or conductance per unit length, and that's G over L. What I want you to remember is that G prime and R prime are not opposite of each other, are not reverse of each other. Can't spell things. Per unit length. And that's Siemens per meter. Okay, let's solve an example and see this in practice. Okay, we have 2 conductors. In between them, there is a material with finite conductivity of sigma. And we want to find the resistance between the conductors. First thing first, I want you to pay attention that this geometry can be, shown in another way. It can be set up in another way. So don't memorize this solution. It always depends how the voltage source is connected to the conductors. That's really what matters, because there can be this, it can look the same geometry, but if the voltage difference is applied in another way, then the calculations are going to be different. Here, the voltage difference is between the inner conductor and outer one. Okay? As you can see, the electric field is shown that is going from the inner conductor to the outer one in R direction, R prime, R hat direction. Radially, basically. Okay? It's asking us to find G prime, which is conductance per meter. Okay? So I'm going to go and see, if I want to find G prime, what I would need. So let's see. G prime, we said, is G over L, because L is the length of this conductor. And then we said G is basically I over V multiplied by L. And here, I is J dot ds. And V here, the voltage difference between these two, is given by VAB. So VAB, I'm just going to put that here. VAB over multiplied by L. Remember that J is sigma E. So sigma is given. The only thing I need to find is E. Right? Perfect. How do I find E? How many ways did we have to find E? Integral, right, of free charges Then we had Gauss's law. The other one was minus gradient of V. Which one should I use here? Please.
Maybe the gradient approach?
What's that?
The gradient approach?
Exactly. E can be written, especially that. It doesn't look like it, but like remember, it's when you have the voltage difference between two equipotential surfaces, it's like you have two boundary conditions. And remember that when we had two boundary conditions, we would solve Laplace's equation. So here we can say E is minus gradient of V. So I need to find V basically. Perfect. For V, I know that Laplacian of V is 0. Are you kidding me? Okay. Laplacian of V is 0. Now, looking at the geometry, which coordinate system should I be solving this Laplacian in? What? What coordinate system? Please. Cylindrical coordinate system. So V generally is a function of 3 variables in cylindrical coordinate system. What are those 3 variables? Three variables of cylindrical coordinate system. What are they?
R phi z.
R phi z. Thank you. Now, looking at our boundary conditions, how can I simplify V? V must be a function of, let's say, one of these. Which one is it? Which one of these do you think it is? V is it a function of phi or z? Anyone else? No? No guesses? So if this is our z-axis, and this is our x and y, like this. Okay? And we know that this is an equipotential conductor. If you know it, just at least say okay, so I don't go back to basics. What is voltage a function of? Now looking at this coordinate system. Is it a function of z? Can it be a function of z? No, right? Because z is changing and our v here is equipotential. Z is changing and nothing is changing. Can it be a function of phi? No, right? Perfect. So v is a function of r. In that case, Laplacian of v is equal to 1 over r, derivative of this, vr. That's the equation for Laplacian of v in cylindrical coordinate system when we only have a component r, a functionality of r. If you want to solve this, then assuming that r is not 0, which is correct because we are solving from a to b, then we can say that this must be the one that is 0. If the first derivative of a function is 0, then we can assume that r rho v is a constant number, C1. So now, derivative of v to r is C1 over r. Now I want to solve this. I want to say that v from point B minus v to point A is basically dr. Basically, the integral of derivative is the same as the function. And this is going from A to B. So this is A to B, C1 over R, dr. This is C1 ln of B over A. VB minus VA, since please notice the polarization here, that is minus VAB. So C1 must be VAB over ln B over A. So we just found that over R is C1, which is minus VAB over ln BA multiplied by R. Since V is only a function of R, then E is minus gradient of V, which is V over R, R hat. And that is going to be VAB over ln BA R. All I did here was to plug in this over here. So we found E. Great. Now, what we need to do is say I is equal to sigma E dot ds. And this is R hat. VAB ln of B over A R, R hat. Now, notice that the electric field is going radially. So the cross-section, the area that I'm considering, is the side of the cylinder. On the side of the cylinder, here, ds can be defined as R d phi dz R hat, where z goes from 0 to L and phi goes from 0 to 2 pi. So what do we get? It's sigma VAB over ln B over A, and R's cancel each other here. Then we get L to pi. So now our G prime, which is I over VAB dot L, is going to be sigma 2 pi over ln B over A. Do you see it? Write it down, and then I move it back. Okay. Any questions? So when we look at, these two conductors, let's look at the cross-section. What we have here is that we have an inner conductor with the radius A, and then we have an outer one with the radius B, okay? And this is a full conductor. In between them, if you look at the electric field we drove, it's 1 over R, R hat direction, basically. So here we can say, okay, if this is the positive voltage and this is the negative voltage, okay, the electric field is going from positive to the negative. So it's going to go like this radially. So in the cross section, the electric field would look like this. Now you're saying, like, you might say, okay, so where is the 1 over r coming to? It shows that if r is smaller, right, the electric field intensity must be bigger. Does my drawing here show that? Does it show it that the electric field intensity is more when radius is smaller? Do this yes, do this if it's no. So you don't have to talk. Does it show it or no? No? How many people? So he's saying yes, you're saying no. Other people? Yes? No? So let's look at it this way. How close are the field lines closer to the smaller inductor here, conductor here? They're closer together, right? Whenever the fields are closer, it means we have more intensity of the field, okay? So if you look at it here, you can see that how much closer they are. And that's a representation of the fact that the electric field is actually bigger when we get closer to the center of this concentric, basically, conductors. So in your exam, you might be asked to draw these, and justify your choices. So I want you to know the concepts behind it. And here you can say that since electric field is going from positive voltage, in a way, you basically have positive charges distributed uniformly on the inner conductor, and then negative ones, again uniformly distributed on the outer one. You can use Gauss's law, actually. This is going to be when we talk about capacitance. You can use Gauss's law to calculate how much charges are going to be on the inner conductor or the outer one, right? We have the electric field. We can say this is our Gaussian surface. The flux going out of the surface must be the Q enclosed in it, right? And then calculate how much Q are being distributed. Okay, I think you guys are tired. We have time if you want to ask questions. I'm here. But yeah, if you want to leave, you can. Thank you.